Hello to everyone. This is an interview for Kappa Center at the Theoretical Department of Physics in the University of Zaragoza. And we have here today with us Ciaran O'Hare, who's a researcher of dark matter, and he's a very active and sparkling young star in this field. So to begin with, we would like to ask you, why did you become a researcher, and to go a little bit further, why did you choose dark matter as your field of investigation?
So I did my degree in the United Kingdom, and I finished my master's, and I sort of felt that I wasn't really done studying. I wasn't really finished with physics. I wanted to know more. I also didn't really like anything else. Nothing seemed very interesting. Physics was just, it captured my attention so much. So, like many people in my situation, I went to do a PhD in the subject. And that's when I sort of really found that I was able to do this quite well, and it was definitely the thing that I wanted to do more than anything else in the world of work. And in terms of dark matter, similarly, I didn't really know what it was specifically that I wanted to research about. I didn't know whether I preferred particle physics or astronomy or cosmology or astrophysics, because I liked all of them and I wasn't particularly good at any particular one. So I think a lot of people have been in the same situation as me, and they've realized that dark matter is the perfect thing to research when you feel like that. Because dark matter, to understand it, it relies on all of those things at once. And you need to learn about bits from a vast range of subjects to be able to understand dark matter and to be able to understand how to detect it in particular. So this is what drew my attention a lot during my PhD, and I haven't really stopped working on this subject since then.
All right. We've been told that you're a musician, so we'd like to ask, does your scientific or mind influence you the way you compose or the way you understand music, or just the other way around? Is your artistic temperament influencing the way you see problems or the way you color your plots?
So as much as I would love to say that it was my scientific mind that influenced the way I composed music or played music in an analytical way or what have you, I think it's actually very much the opposite way. I think it's the fact that I have a musical brain or more of an artistic brain than a scientific or an analytical brain, which infects the way that I do science. And a lot of the time when I am doing science, it feels very improvisational, very chaotic. A lot of the times I'm just using past experience to just throw things at the wall or just try different things. And I very much like working like that. It may seem incomprehensible to a lot of other scientists who like things to be a lot more organized. But for me, it works very well. Maybe it makes me a horrible person to work with, but this is the way I like it. And certainly with the way I color my plots, thank you for the plug to my plots. I spend a lot of time on them, probably more time than is really necessary, making sure that every color is correct, and I have all of my RGB values correctly specified in my Python script. So yeah.
All right. Okay. So let's focus on the storm. First of all, we want to know what is a storm of dark matter and what was its cause.
So this is all coming from a recent paper that myself and some collaborators wrote called A Dark Matter Hurricane, which is a slightly tongue-in-cheek title for what has recently been discovered in the Gaia data of a stellar stream that is intersecting our location. So Gaia is the most recent astrometry satellite that has surveyed 1.7 billion stars or something like this, and is giving us a transformational view of the Milky Way. And we've observed a lot in the Gaia data, and one of the most remarkable things that we've seen recently, or some collaborators of mine have seen, is a stream of stars that intersects our location. So a stream is basically the relic of a smaller dwarf galaxy or dwarf spheroidal or globular cluster which has been absorbed, or is in the process of being absorbed and tidally disrupted by our Milky Way. So what we are inside of is the relic of one of these streams of stars. Now, typically, streams from objects such as dwarf galaxies or dwarf spheroidals will have come from objects which have dark matter associated with them. So it's reasonable to expect that this stream of stars, this S1 stream that we're inside of, also is bringing with it dark matter. Now, the interesting thing about the S1 stream is that it is counter-rotating in the galaxy. So we are spinning around on the Milky Way disk in a particular direction, but the stars are going in a retrograde orbit. They're going in the opposite direction. So it means that the speed of the dark matter associated with the stream will be very high. It'll be around 530 kilometers per second. So rather than the dark matter wind, which is a phrase that we often use in the context of direct detection, it's a phrase that we often use in our community, we decided to change that to dark matter hurricane, because there's this extra, a very fast population of dark matter particles, in principle, entering our solar system. So it was a slightly tongue-in-cheek title. It was meant to gather the attention of people reading the archive, reading the sort of the daily updates of papers, but it managed to attract a decent amount of media attention as well.
So it's like a colloquial name.
Yeah, it's a bit of a joke. It's a bit of a joke name it is quite common for us to do, actually, because there are so many papers that come out every day. It's becoming more and more common for people to come up with like a little catchy slogan for their paper or some kind of silly titles. Most of the times, the journals will just throw away these titles. Say you can't call your paper this. They'll change the title to something boring. But for whatever reason, they liked the hurricane and they let us keep it, and then this happened.
So, what kind of information can we get from the storm, and how do we get this information?
So the thing that we are really interested in are the consequences of the S1 stream on dark matter experiments. This S1 stream is really going to be relevant for experiments on Earth, so the experiments that are looking to directly detect dark matter. So what we had to do was to think about what are the consequences of the stream in all of these experiments. And for the case of WIMP dark matter, it turns out that the consequences are quite mild, and in fact, it's hard for these WIMP experiments to be able to tell the difference between whether or not the stream was there or not there. If you have a more sophisticated type of experiment called a directional experiment, it becomes a lot easier. The really interesting thing, though, was with the axion experiments. So the characteristic of the stream is that the speeds of the dark matter particles are concentrated around one value. It's a very cold feature. And axion experiments are very sensitive to cold features because they are sharp spikes. They're sharp signals with very sharp spikes. So it actually turns out that for certain cases, for certain models, the S1 stream could make the axion easier to detect. So if the S1 stream was particularly strong at our location, we could detect the axion earlier than we would have otherwise. So this is very interesting. But the thing that we need next is to detect dark matter. Everything has to start at that point.
All right. We've been told, our teachers have been told, that there are axions, there are WIMPs, there are primordial black holes, and many other candidates to be dark matter. So we would like to know, for you, which is the most suitable candidate to be this dark matter that we want to find.
So I think if I knew the answer to that question, I would have information that other people don't have. At the moment, we don't have any real hard evidence in favor of any particular dark matter candidate over another. The things that you can talk about are aesthetic qualities of dark matter models. So dark matter models which have nice theoretical properties, they come from a well-motivated place. And I think a lot of people in our community would argue that the axion, the QCD axion, is the best particle in terms of aesthetically speaking, in terms of these questions. The reason is because the axion, as well as being a very good dark matter candidate, it also solves a completely separate problem in particle physics, the strong CP problem, and that was the problem it was designed to solve. And the dark matter was something that was realized afterwards. And I think this is, from a purely aesthetic point of view, not really a hard statement scientifically. This is very nice. This is a very nice thing that the axion does. It's why it's becoming so popular. WIMPs could be argued have or had a similar argument that you could play, but one of the things that we really needed was to see some signal of supersymmetry in the Large Hadron Collider, and this has not happened. And over maybe the last 5 or so years, there's been a real burst of excitement around the axion for this very reason.
All right. So when you talk about axions, we can hear solar axions, black hole axions. Are they the same or are different?
So in terms of the particle, they are all the same particle, but they are produced via different mechanisms. So the axion that we're looking for in our dark matter experiments, these are relic axions. They were produced after the Big Bang. There are lots of uncertainties about how they were produced. These are questions that are being actively worked on. But these axions, the dark matter axions, are relic axions. They're coming from the early universe. Solar axions are axions that are produced in the sun's core. So it's the same particle, but it's produced by a different mechanism, and they have completely different energy spectrums. The dark matter axions are very cold. The axions coming from the sun are relativistic, and you can detect them in similar types of experiments, but the experiments have to be set up in slightly different ways in order to detect them.
Okay, and for finish, how do you see the near and distant future of dark matter and dark matter astronomy?
So, in terms of dark matter detection, I think we're at the cusp of what is going to be a new phase of experiments looking for, particularly WIMPs. We are just at the beginning of what you could say is the next generation. The leading experiments looking for WIMPs are xenon experiments, and LZ and xenon. The LZ and xenon collaborations are entering a big upgrade, and this is going to be exciting. For me, it's incremental progress in a particular range of the parameter space, which was historically very interesting from a particle physics point of view. For the axion world, there are lots of things on the horizon that are going to take a bit longer to really come to fruition. But one of the really exciting things is there are now so many. I mean, maybe a little bit further in the past, there are maybe just a couple of groups on their own in this sort of wilderness of the axion, the available axion parameter space. And now, although the experiments are, in comparison to the WIMP experiments, they're made by small groups of people working in a completely unknown area, because there are so many groups all working at once, all attacking this very well-motivated particle. This for me is the most exciting, and exciting just because there's so many independent groups. And this is, I think, what we have to look forward to in the next 10 years. I can't really say if dark matter will be detected in the next 10 years, but I think we all sort of hope that's going to happen.
We will see.
We will see.
All right, that's all. It's a pleasure having you with us.
Thank you very much. It's a pleasure.
Thank you very much for your time.
Cheers.